All right, folks, welcome back to our third presentation on soil colloids. Today we're going to be focusing on soil pH. So the general concept of pH is basically on a scale, okay? So it's based on the sources of soil acidity, and we're going to talk about the role of protons and aluminum in soil acidity, and some of the human and natural influences on pH. We're also going to go over a concept called buffering capacity and adjusting soil pH, kind of the chemistry of how it works. So all of these soil objectives are basically based on what I just discussed. Basically, given the concentration of hydrogen ions in a solution, I want you to be able to calculate the pH. Many soils tend to become more acid as time passes, so I want you to be able to identify the sources of their added hydrogen ions, and there'll be a list that we'll go over for that. Um, we're going to talk about how the leaching loss of cations can acidify soils over time. I want you to be able to explain that. I want you to be able to compare the four principal pools of soil acidity: active, exchangeable, residual, and potential. Um, we're going to talk about the influence of soil acidity through nitrogen fertilization and acid rain. I want you to understand low soil pH conditions and how various nutrients can then become toxic to plants because of that. In addition, other valuable soil nutrients like nitrogen, phosphorus, and potassium become less available to plants in these conditions. So this is why we lime soils. I want you to understand that process and how liming materials do their job. We're going to identify four key factors influencing the amount of liming material needed to correct acidic soil conditions. And we're going to talk about some of the plants that naturally enjoy acidic soil conditions as well. So what does pH mean? It's basically the negative logarithm of something. All right, so in this instance, it's the negative logarithm of the concentration of hydrogen or proton ions in solution. And so ultimately, what we get is 10 to the negative number something in terms of the hydrogen ion concentration. And so this makes it actually really easy for you to calculate because basically it just means that whatever is in that parentheses, 10 to the negative 6, pH is 6. 10 to the negative 5, pH is 5. 10 to the negative 3, pH is 3. 10 to the negative 8.5, oh yeah, it's 8.5. That's the pH. All right, so it becomes pretty straightforward. But if you were confused in any way, shape, or form, you could type in the negative logarithm of whatever that number is into your calculator, and it would give you the pH. So what we know about pH is that as pH drops, as it becomes more acidic, our hydrogen ions increase, versus as pH increases, our hydroxide ions increase. So there's an inverse relationship between the amount of hydrogen ions and hydroxide ions. When hydroxide ions are high, pH is high. When hydrogen ions are high, pH is very low. And when they're equal to each other, pH is 7, and we consider this neutral. So some soil pH descriptions. Anything below 5.5 we consider to be very strongly acid. 7 is neutral, and above that we consider everything to be alkaline or basic or to have a higher pH. Below pH of 7 we consider it to be acid on a variety of scales. So one of the things I won't ask you on an exam is what is the pH scale for slightly acid? Like, I'm not going to ask you that. I don't need you to know the specific names for pH numbers. What I do want you to be able to do though is if I give you a hydrogen ion concentration, I want you to be able to tell me what the pH is. So if I say we have a hydrogen ion concentration of 10 to the negative 7, I want you to be able to say, oh, that's a pH 7. And I want you to understand that 7 is neutral, below that is acidic, and above that is alkaline or basic. So those are the basic principles I really want you to understand from these slides. But here on the right in figure 9.2, you can see some the pH scale for a variety of common day things. So pure water and milk both have a neutral pH of 7. Beer and coffee are in the pH scale 4 to 5, so they're considered acidic along with vinegar, lemon juice, and battery acid, which is very, very acidic, being very close to 0. Bleach is actually very alkaline, very, very high pH. Antacid tablets have a pH of 9. Seawater, baking soda have a pH of 8. Very alkaline. All right, so the sources of hydrogen. This is very important. You need to know this list. Write it down and study this for the exam, okay? Hint, hint, hint. This is on the exam. You will have to list these. All right, so the sources of protons or hydrogen ions that make soils acidic, okay? Carbonic acid, organic acids, organic matter, nitrogen oxidation, sulfur oxidation, acid precipitation in the form of rain, and the plant uptake of cations. What's interesting about the plant uptake of cations is that in order for a cation to cross the membrane into a plant, like a plant root, it actually has to have like some carriers, and it ends up acidifying the rhizosphere. So very interesting, especially, well, we'll talk about that later. So I'm going to stop there. But anyways, plant uptake of cations, very exciting. All right, so how do soils become acid? Well, during the acidification of soil, we essentially have a clay colloid, and it has all these exchangeable cations on it. And over time, protons are added in from acid-forming processes like that list we just discussed, and they exchange for our base cations on the exchange side. So the two protons come in this instance, and they kick off a calcium and displace it, and the calcium goes on and is lost through leaching. Okay, and so over time this happens again and again and again, and ultimately it causes soil to acidify. And so this acidification of soil is an important process for you to understand, because when soils become too acidic, they're no longer as productive or as useful for a variety of the purposes that we need them for as when they were less acidic. Okay, so we'll talk about that a little more. But let's first talk about the pools of acidity. So we've talked about the sources of acidity, we've talked about the acidification of soil, and now we're going to talk about the general pools of soil acidity. Okay, and so we have residual pool, we have an exchangeable pool, and we have an active pool. So let's take a look at these in terms of this figure. It kind of helps to drive home the point. So the residual acidity is the aluminum and hydrogen bound on the clay surface or to the surface of humus. Okay, and so these ones are really, these are like your savings account. Okay, they're something that you don't touch as much, right? So they're a little more tightly bound. And then we have our salt replaceable pool, which is on the exchangeable area. Okay, so this is like cash in your pocket. We have a variety of ions held near the clay and humus surfaces, and they're a little more easy to spend because, again, oh, sorry, not cash in your pocket. This is your checking account. They're a little more easy to spend. You can withdraw as you need, but hopefully you don't overdraw. Anyways, moving on to active acidity. These are the ions in solution. This is the cash in your pocket, okay? So this is very easily spent. It's not really attached to anything, just hanging out in your pocket, okay? So active acidity are ions in solution, cash in your pocket. Salt replaceable or exchangeable acidity are the ions held near the surface. They are exchangeable. They are, it's like having money in your checking account, okay? You can spend it, but you do have to, somehow access it first. And then your residual acidity is bound to clay and humus, and it's like your savings account. Not that any of us have savings account, but let's all pretend that we do. And this is the money that you don't touch unless you absolutely have to, until you've spent the cash in your pocket and you've spent the um, cash in your checking account, and then you go to your savings, right? So this is the last pool to resort to. All right, so we've got these three pools: active, which is in soil solution; exchangeable, which is on your cation exchange sites; and then your residual, which are non-exchangeable. They're really stuck to the surface of clay and humus. We also have like some potential acid that comes from, like, if there's sediments that are laden in pyrite, for example, but we don't really pay attention to that pool very much. So the total acidity is the addition of all of these things. Okay, so this is the potential for soil to be acidic. And why this becomes important is if we want to change the pH. Okay, so if we know the pH is too low, then we're going to add something called lime to the soil to bring that pH. But first we have to satisfy all these dang pools of acidity, because the soil is kind of tricky like that. All right, so we'll get back to that idea, just kind of planting some seeds. Aluminum and acidity. Aluminum is basically the cation of a weak base. Okay, so we see the hydrolysis of water here being the cation of a weak base. And as pH increases, aluminum can release via hydrolysis 3 proton ions. Okay, so that basically means that it's very resistant to changing pH. As pH tries to go back up, aluminum's like, no, 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 no. Okay. So we also play a role in soil acidification. Um, when we fertilize for nitrogen, it causes acidification in the soil, and acid rain can also lead to acidification of the soil. So as we talk about nitrogen fertilization, you don't have to know this equation, it just kind of like helps paint the story. Nitric acid and sulfuric acid are very strong acids, meaning a strong acid basically very readily releases its protons. And as we know, when protons are available, things can easily turn acidic. So we can acidify the soil solution, right? Only when we excessively fertilize for nitrogen does it cause acidification. So if we're over applying nitrogen, we are causing excess acidification in our soil, which will later require us to excessively lime it, and it just wastes money. So this is not something that happens as much anymore, hopefully, but we are trying to educate farmers on this as much as possible. Here you can see two plants, and you can see on the left that the proton is consumed and bicarbonate is released, whereas on the right we see a significant amount of proton release when ammonium is added instead of nitrate to the soil. So what this basically tells us is that the type of fertilizer matters. When we add nitrate as our form of nitrogen in fertilizer, we see less acidification versus when we add ammonium, which ultimately acidifies the rhizosphere quite a bit faster. So there's of course a human role in soil acidification, because for all of our brilliance and wonderfulness, we do kind of suck sometimes. So nitric and sulfuric acids, basically released into the atmosphere via industrial processes, can account for 30 to 80% of acidification of soils in human regions. We're a human region. So of course, all the environmental acts that were passed that will hopefully continue to be in existence, um, that protect the clean air, like the Clean Air Act, etc., all of that has helped to cut this down, but we definitely don't want to go back to that, because that was a huge issue for a lot of our soils. In fact, what we found since all of those environmental protection acts were passed is that now our soils are actually starting to have a sulfur deficiency, because we're not getting so much acid rainfall adding sulfuric acid into soils and therefore providing sulfur. And so we're actually having to start to add sulfur ourselves. And frankly, I think this is a good thing because that means that our air is cleaner. So anyways, this soil acidification from acid rain is, essentially from fossil fuel combustion in power plants and vehicles, and the smelting of sulfur containing ores and forest fires, which of course we've had quite a few of those lately, so could definitely see some deposition of some sulfur. Essentially, mm, soil is a weak acid system. Okay, so there's dissociation as protons increase, the reaction moves to the left and the weak acid consumes a proton. Okay, so we have all of those pools of acidity that we have to overcome before we can change the pH. And as we try to overcome them, there's yet another one that we'll encounter. So first of all, there's the soil solution pool, right? And we can add in something to change the pH, and we think we've changed the pH because we're measuring the soil solution. And then that middle pool throws out some protons and changes it right back. And it can keep doing it until those two pools are exhausted. And then we still have that third pool that can come out. So soil's sneaky in this way. So we have to overcome this buffering capacity. In order to minimize large changes in soil solution pH, we have to overcome the buffering capacity. We have to remember that buffering capacity increases with increasing cation exchange capacity. So remember, cation exchange capacity is the number of exchange sites available on a soil. So it's basically telling you how many parking spaces there are for protons. It's kind of like having a whole bunch of pools that you have to drain before you can refill them with the right solution. So ultimately, there is an effect of pH on the availability of nutrients in plants. And this is why we care about all of this, okay? So as you can see, the pH scale is on the top of this figure. It ranges here from 4 to 9. Most of the plant nutrient bars there are thickest between pHs of 5.5 to 7.5. Okay, with some exceptions. For example, iron and manganese are super high, and zinc could potentially be said high, and fungus are high at lower pHs. And at higher pHs, calcium, magnesium, and molybdenum are made available. But for the most part, all of our essential nutrients are widely made available between the pHs of 5.5 and 7.5. And so that ends up being, we'll just say 6 to 7, ends up being our ideal range. Okay. So we'll just say, for the sake of keeping it simple, that somewhere between pH of 6 and 7 is the ideal pH range for growing plants in terms of nutrient availability. Now, this does not mean that all plants require this range. It just means that this is where most of the nutrients like to be. So for example, blueberries love acidic soils. So they're an anomaly here, right? Like we wouldn't want a lime soil to grow blueberries. You always want to look up the pH preference of whatever plant you're trying to grow. But for the most part, most plants enjoy being in this middle range. There's also this weird thing with pH where we can have toxicities at too low or too high of a pH. So what we see with aluminum is that plant roots are really, really, really small because they're basically getting burned and can't keep growing when aluminum is very high. So the roots of plants grow a lot longer where aluminum is low. And aluminum happens to be one of the things that increases when we have acidic pH. So if you have a plant that in which most plants, I think there's only like one or two plants that can withstand a lot of aluminum. Um, if you have a plant that is aluminum sensitive, which is basically every plant, you would want it to grow in soils with low aluminum content, which means you want it to grow in soils that have moderate to decent pH. So we also have an issue with manganese toxicity in wet soils with low pHs. Okay, so especially for beans and cabbage. This can negatively affect yields, as well as aluminum and manganese can also affect taste. Some nutrients in excess can affect taste, and that becomes very important, especially in like the grain industries, especially where we're growing hops for beer. The nutrient loads and carbon and nitrogen contents and a few other ratios in the grains becomes very important. If you have too much of one nutrient, it can make it excessively bitter or it can mess up the flavor. So lots of little things, lots of little details that we have to pay attention to. There's microbial effects, of course. Nutrient impacts are very similar. So for example, in very low pHs and acidic pHs, fungi will dominate the soil. So this is a great example. In forest soils, they're usually acidic and they're usually dominated by a fungal environment. And in neutral to alkaline soils, bacteria will dominate the environment. And this doesn't mean that it's all bad stuff. Most of the time, it's good stuff. So in acidic forest soils, mycorrhizal fungi will probably dominate the landscape. And that's a good thing because it's been shown to send nutrients and allow for like a communication pathway between trees for miles and miles and miles. Pretty crazy. A lot of bacteria are basically responsible for converting nutrients into the plant available form. So we like when bacteria are present. Of course, there are some fungi and bacteria that we don't like, but as long as we have a healthy soil, then we have a healthy ecosystem with a natural balance of predators and prey. So let's talk about the types of liming materials that we can use to ultimately change soil pH. There's calcitic limestone, dolomitic limestone, burned lime, which is the oxide of lime. So this is kind of like, um, oh, I'll get to there. Never mind. Hydrated lime, which is a hydroxide of lime. Basic slag marl is something that's mined from shallow coastal beds, dried and then ground before use. It also is often mixed with soil or peat. Wood ashes. So these are pretty popular in like smaller gardens or um, older agricultural methods. You'll hear of people using the wood ashes from their fireplace around their fruit trees and in their gardens. And I do this as well on a small scale. It's pretty easy to do. Miscellaneous lime containing byproducts. A variable composition, but you always want to test for toxic impurities in these kinds of things. Um, because if you're using some kind of miscellaneous product that contains lime, that means it contains other things as well. So you want to make sure before you add it to your food plot that it contains things that are okay for you to use with food. AKA read the label, my friends. Read the label. All right, so how do liming materials actually do their thing and get to where they need to go and raise the pH? This is a quarry showing people actually. All right, so reactions of liming materials. Ultimately, all the materials neutralize 2 protons per molecule of liming agent, okay? So ultimately, we add in some calcium oxide, turns into a calcium dihydroxide kind of form, and that breaks down into a hydroxide and a calcium molecule, or magnesium carbonate added with water and carbon dioxide breaks down into bicarbonate magnesium, and the calcium and the bicarbonate displace the hydrogen ions that are on the surface of the soil colloid and replace it with calcium. And those protons are then absorbed as water, and the CO2 is lost to the atmosphere. So ultimately, when we started out with a proton that was acidic, and I'm sorry, that when we started out with a colloid that had a lot of acidic protons at the surface, it's replaced with calcium, and those protons, instead of just being kicked off to the soil solution, instead they're absorbed and basically creating water. So, kind of a cool process. All right, so determining limestone requirements. What is the magnitude of the application? So to determine how much lime we need to add to overcome all those pools of acidity, we've developed a series of tests to test the soil to kind of calculate how much lime we actually need. The Socorro buffer test was invented in Kentucky at the University of Kentucky, alma mater, and that basically determines pH in water. And then we use an equation or a table to determine the lime rate based off of this test. So we need to know our current pH and what we want it to be. We call this our target pH. So you need to know your current pH and then your target pH. We need to understand the buffer capacity of the soil, which is where the Socorro buffer test comes in. And then we want to know our liming material characteristics. What is the chemical form? What is the purity of lime? And how small or what is the fineness of the lime that we're using? Because as you've learned in this class, particle size makes a big difference. The smaller and more fine the material, the more surface area and reactivity, and so therefore we will need less of it. You don't want to overlime your soils, friends. I know it may seem, well, might as well be safe and throw out extra. You don't want to do that. If you overlime your soil and you make the pH too high, it's significantly more expensive and significantly harder to acidify soil than it is to increase pH. So please remember that. This is especially important for small garden plots. A lot of people overlime small garden plots. Um, Please don't do that. It is better to underlime than overlime always. It costs a lot of money to acidify soil, and it's a very long process. All right, applying the material. So lime is a slow-acting material, so we only have to do it every 3 years or so. We want to do it about 6 to 12 months prior to the highest need of the crop. So you'll see a lot of people are liming right now in the fall in preparation for planting in the spring. We usually incorporate it at about 6 to 8 inches if you're in a tillage operation. Otherwise, you can surface apply it and hope that it moves throughout the soil profile evenly in no-till operations. So other methods of changing the pH, but in this instance, we're trying to lower soil pH. Okay, so we've been talking about how to increase soil pH by liming it, measuring soil acidity, et cetera, et cetera. Now we are in a situation where we have too high a pH. Maybe we bought a farm and the soil pH, there's a lot of calcareous parent materials and the soil pH is naturally at about 8. So how are we going to lower that to that range that is ideal for production? We can add compost and mulches from coniferous trees because the pine needles add acidity to the soil. We can add acid peat moss. But remember, when you add these materials, you want to make sure that you're careful about your nitrogen requirements because it's very easy to acidify soils and lose that nitrogen or in some cases over apply nitrogen. So again, we have to have a balance. There's also inorganic amendments like adding elemental sulfur or adding ferrous sulfate to iron-loving plants. These will naturally acidify soils.